Thermodynamics is the study of energy and its transformations, and a subcategory of that would be thermochemistry, where you are looking at chemical reactions and their energy changes. In chemistry, we are interested in those energy changes through chemical reactions. Potential energy, this is energy due to composition or position. In physics, they more study gravitational positional energy, but in chemistry, we're looking at the bonds in a chemical reaction. Kinetic energy, this is the energy due to motion, due to the molecule, due to some sort of chemical reaction. So down here we have a cannon, and in the gunpowder, when the activation energy is added to the gunpowder, that spark, then the gunpowder can combine with oxygen and we can have a combustion reaction. So we have that chemical potential energy that then is converted to work. It pushes that shell or that cannonball away from the cannon, and so we see that here we have chemical energy. It is then converted to kinetic energy. And overall, you should know that energy cannot be created nor destroyed. This is known as the law of conservation of energy. So the energy just changes forms, might change from a potential energy to a heat energy, for example. On your data sheet, you are given this formula. Kinetic energy, or this energy of motion, is equal to 1/2 mv squared. You will never solve a problem for kinetic energy, but you just need to know relationships. First of all, mass is m and v is velocity. To measure the kinetic energy, we actually use temperature. Temperature is a measure of the average kinetic energy. Essentially, when we're talking about temperature, we are talking about kinetic energy. Now, in the class, I passed out a popsicle stick, and we can use this popsicle stick like a seesaw to see some relationships. How you set it up is you put kinetic energy, which remember is temperature, on one side, and then mass and velocity on the other side. Because mass and velocity are on the same side, they have an inverse relationship. One thing that you should know, that if all molecules in a sample are at the same temperature, they will all have the same kinetic energy. So the smaller the mass, the faster the molecule will travel in that sample. So let's look at this problem and use the popsicle stick to help us find it. So you could just look at the equation to see that inverse relationship, but sometimes it's nice to use the popsicle stick to see an example of what's going to happen. So looking at this problem, so it says at 20 degrees Celsius, which molecule has the fastest velocity, nitrogen or the chlorine? So because kinetic energy, mass is important, I'm going to go ahead and find the mass. So nitrogen would be 2 times 14 or 28, and then the chlorine is going to be 71. And again, that's looking at the periodic table. So I know that this one is going to be larger and this one's going to be smaller. And it says at 20 degrees Celsius. So they're both at the same temperature. So I'm going to put my finger right here on the popsicle stick, right over the kinetic energy. So this creates a little seesaw. Then I know that if my mass is higher, so if my mass goes up, then I will see that the velocity or the speed goes down. And again, this is when they're at the same kinetic energy or the same temperature. What that means is your smaller molecule is going to move faster and your larger molecule is going to move slower. And this is at the same temperature. We have done Maxwell-Boltzmann plots before. And if I just sketch it out over here on the right hand side, so at 20 degrees Celsius, we see that nitrogen and the chlorine gas, they do have a distribution of speeds. So nitrogen does have some right here that are going slow, and it has some over here that are going fast. But overall, when you take the temperature, you get an average. So an average, a little glimpse of their speed. And we can see that overall nitrogen has molecules that are moving faster than chlorine, because chlorine's average speed would be over here. Again, chlorine would still have some going slow and some going fast, but its average would be much lower as far as its velocity. So that's just one thing to know that you can get from this kinetic energy equation, that the larger the molecule at the same temperature, the slower it's going to go, and then the smaller the molecule, the faster it would go. And this is at the same temperature. Let's go ahead and do another relationship. So let's look at this problem. Nitrogen and chlorine are traveling at the same velocity, which has the most kinetic energy. So this time on my popsicle stick, I'm going to put my finger over the velocity. So that stays the same for both of them. And it says which has the most kinetic energy. So if my popsicle stick goes up with the mass, so it'll go up like this, I see that as my mass goes up, my kinetic energy will also go up. Therefore, I know that the one that has the most mass is going to have the most kinetic energy. And mathematically, it would work out if you just made up some numbers for the velocity. If they both had the same velocity, you would see that the one with the greater mass would have the most kinetic energy. So you could figure that out mathematically too. So my answer would be chlorine in this problem. Potential energy is a stored energy, and in chemistry, the chemical potential energy is due to electrostatic forces between the charged particles. So this just boils down to Coulomb's law. Like charges repel, unlike charges attract, and distance is important. So we can apply that to this diagram that looks at the force, the repulsive forces versus the attractive forces. When we have two ions that are widely separated, there's little attraction. But as we get them closer together, then we see that there is an attractive force there, and then there's a sweet spot, kind of the Goldilocks spot, where it has equilibrium with attraction and repulsion. And then if they're too close together, their electron clouds are going to overlap, and you're going to get more repulsion forces. So as far as the distance you're going to find each of the nuclei away in a bond, it would be right here. And it all has to do with the attractive versus the repulsive forces. And so this all ties into potential energy. There is a difference between temperature and heat. Remember, temperature is a measure of the average kinetic energy. We just got done talking about that. Heat is the energy that is transferred when there is a temperature difference. So heat is a combination with how fast those molecules are traveling or how fast they're vibrating, and also how many are present. So do you have a small bucket of hot water versus a large bucket of hot water? The larger bucket would have more heat. And that is because there's more mass there behind it. Remember that heat always flows from the hotter object to the colder object. So a lot of times you hear people say, oh, my hands, they got cold. Well, that is actually incorrect. So cold cannot travel. So cold cannot travel into your hands. Instead, what is happening on a cold winter day when your hands feel cold to you, what's happening is the heat is leaving your hands. And so your brain is interpreting that as it's cold. My hands are cold. So heat can travel, cold cannot travel. Let's discuss the heat transfers taking place in each of these situations. So first of all, we have a hot cup of cocoa on a cold winter day sitting on a picnic table. The heat transfers, there's lots of them. I can get heat traveling out through the cup to the surrounding. I can get heat traveling from the cup to the napkin, then to the picnic table, and I can also have it directly to the air. And when you go and look at the molecular level, you'll see that those water molecules, they will cause the glass molecules to vibrate, and they will vibrate faster as they are warmed up. And then when your gas molecules come close, they will pick up some of that energy, and that will result in them traveling faster. And the same thing here with the bottom of the cup. The gas molecules, they vibrate faster. Then you have your napkin molecules, they will vibrate faster, and then even under that, the table molecules. So you see that the kinetic energy, or that heat energy, is being transferred through collisions. The opposite here is this is a summer day with a cup of ice cold lemonade. The heat transfer is taking place because it's a warm day. The heat is going to go into the cup, so eventually you will see the heat causing that ice to melt, and this time it can come up from the picnic table. For example, the picnic table molecules can vibrate faster, then you get the glass molecules of your lemonade, and then last your water molecules, your lemonade molecules, they will start moving faster. So, and again, remember, heat transfers, and it always goes from warmer to cooler. Please pay attention to your units of energy. The joule is the standard unit of energy, and it's just given the letter capital J. And a joule, because it's such a tiny amount, often the AP board likes you to use kilojoules. So just pay attention to what they ask for. One thing I do know is that if they ask for kilojoules and you give the answer in joules, as long as you have that J there, they will give you credit. So if they ask for kilojoules and you only go to joules but you don't put a unit there, they will not give you credit for that. Just make it a policy that if you are doing joules or kilojoules that you write a J or a KJ after your answer. All this stuff down here you don't need to know. This is not on the AP test, but it's just a point of interest. We, in our day-to-day energy needs when we eat, they are measured in calories. This actually is a nutritional calorie with a capital C, and it is 1,000 normal calories. So 1 calorie is equal to 4 joules about. And so when we are eating, we're actually consuming units of kilocalories, which they give as a capital C. When we work with joules in the lab, just know it's a really tiny unit, and just pay attention if they want joules or kilojoules. Internal energy is the sum of all kinetic energy and potential energy. Energy is the capacity to do work or to produce heat, and work is the force acting over a distance. As far as solving for problems with work and heat, I've never seen them ask this, but it does go over it in one of your chapters. So I just want to briefly mention it. In chemistry, we are mostly interested in the change in energy. So we will see these little deltas. Whenever you see that delta, it's a change in the enthalpy or a change in the heat, and it's always final minus initial, or it's products minus reactants. The law of conservation of energy says that energy can be converted from one form to another, but it can be neither created nor destroyed. And the first law of thermodynamics says that the energy of the universe is constant. Chemical changes are always accompanied by a change in energy. And so generally we are looking at what's called a system. So this would be our chemical reaction that we're looking at. But the chemical reaction or the system plus the surroundings makes up the universe. So when we're looking at a chemical reaction, we're actually looking at a really small section of the universe. Everything's at the point of view of the system of the chemical reaction, and everything around it, outside of it, is the surroundings. So let's look at this diagram over here on the right. So when I go to look at the system, what's happening, I can't measure what's going on with the system directly, but I can use a thermometer to measure what's going on in the surroundings. So I use what is going on in the surroundings to figure out what's happening to my system or to my chemical reaction. Let's say that I see that my thermometer is rising and it gets really high. This means that in the system, heat must have left the system or left that chemical reaction and gone into my surroundings. So this would be an exothermic reaction, or energy exits that reaction. Endothermic would be the opposite. The energy would go into the reaction. So I would see in my surroundings the temperature goes down because the heat is going from the surroundings into the system. So again, exothermic means the heat leaves the system, and so we measure our surroundings getting warmer. Endothermic means the heat is entering the system, and we measure our surroundings, the temperature decreasing. You should know to draw an exothermic potential energy diagram, so something that looks like this. The reactants are at a high amount of potential energy. The products are at a low amount of potential energy. Activation energy is required. So you start with your reactant line and you go up to the top of the little energy hill, and this is your activation energy. The activation energy is required to make this activated complex. That's where the bonds are broken and reformed. And then we go down the energy hill to our products. The difference between products and reactants would be our enthalpy. Because our products are a lower number compared to the reactants, we are going to get a negative number. So delta H will be negative. And this describes the amount of heat that has left the reaction. In an endothermic, this is the opposite of the exothermic reaction. Our reactants start low. Here's our activation energy to make that activated complex, and our products are a higher amount of energy. So we see that energy is absorbed. This comes from the surroundings. And because I have my products minus reactants, and products will be a bigger number than the reactants, then I end up with a positive number. So my delta H will be positive always for endothermic. So you should know how to sketch a potential energy diagram for exothermic or endothermic, and also tell the sign of that delta H. Delta H negative, the enthalpy, that would be exothermic. Positive would be endothermic. And I always remember that enthalpy is an H because there's an H in the word enthalpy. So that H is the symbol for the change in enthalpy. So remember, exothermic and endothermic, it depends on the system or what we're looking at. And so in each of these examples, I underlined what you should go from what point of view. So in A, your hand gets cold when you touch a metal rod. So because my hand is losing heat, so this would be an exothermic reaction. The metal rod gets warmer when you touch it. So if the metal rod is the system and the heat is coming into the metal rod, then this would be endothermic. The heat is going into. Water boils in a kettle being heated on the stove, so the heat is going into the kettle, which is going into the water. So this would be an endothermic reaction. Water vapor condenses on a cold pipe. So the water vapor is losing heat and it's going from a gas to a liquid. And so because it's losing heat, that would be exothermic. And ice cream melts. So the reason it's melting is because heat from the room is going into the ice cream. And so that would be an endothermic reaction. A property of the system that depends only on its present state is called a state function. So in other words, if I was looking at this water at 25 degrees Celsius and I have 50 grams of it, I could have gotten to 25 degrees Celsius starting with ice and then heating it up to get to the 25 degrees, or I could have started with a temperature of 100 degrees, so right at the boiling point, and then cool it down to get to the 25 degrees. But if I'm analyzing just the water at the present state, then it doesn't matter where it came from. So in other words, it doesn't have a memory that it came from boiling water or it came from ice water. It is just 50 grams and 25 degrees Celsius. When we look at work and heat, it is not a state function. It does depend on the path, and so that's why we have exothermic and endothermic reactions, because the path of showing where that heat is flowing is important. As I said before, units are important. You can let your units guide you, especially in these thermodynamic problems. Let's look at this problem. When 5 grams of methane are burned, 150 kilojoules of energy is released. What is the delta H of combustion for methane in kilojoules per mole? So you may not know what the enthalpy of combustion means, but you do know what units they give you. And so that is your formula. So I'm just going to find kilojoules, and then I'm going to find moles, and then I'm going to divide, and then that will be my answer. My kilojoules are given to me, and my moles are not. I would have to convert my grams to moles first. So let's quickly figure that out. Using a periodic table, I see there's 16 grams per mole of methane. And so when I divide 5 by 16, I get 0.3125. So kilojoules on top, moles on the bottom. I just have to divide it out, and I get 480 kilojoules per mole. Let's just double check that we have sig figs. We start with 2 sig figs, and our answer has 2 sig figs, so we're good there. So this is a chemical reaction that powers the liftoff for the space shuttle. So we take oxygen and hydrogen gas and we combine them in a synthesis reaction to get water vapor. And this is how much energy we get from this reaction, and that little negative sign tells us this is exothermic. So I can put plus heat because heat is a product. I can actually use that delta H, that enthalpy, as a conversion factor because 2 moles of hydrogen give me 483.6 kilojoules. And we can see the same thing for the rest of them. So if I had oxygen, I would know that 1 mole of oxygen would give me that amount of heat, and 2 moles of the water would give me that amount of heat. So we can use this to do some calculation problems or some stoichiometry problems. So what is the enthalpy change, so my delta H, when 178 grams of water are produced? So I'm going to start with my 178 grams. And I'm going to convert to moles because I know what my molar ratios are. So now that I have moles of water, I can use that balanced equation to help me convert to energy. So 2 moles of water to my minus 483.6 kilojoules. And when I do all the math, 178 times 1 divided by 18 times negative 483.6 divided by 2, I get a negative 230 kilojoules. And let's just double check sig figs. So sig figs, there's 3 of them, so I'm going to just round it. Let's do one more of these conversion factors where we look at the heat. This is the combustion of propane, and I know that because delta H is a negative, that this is an exothermic reaction. So the heat is a product. So I have this amount of heat that is going to come out of it. And it says how much does 5 grams of propane burn? How much heat do we get? So I know that 1 mole of propane gives me this amount. So that's the conversion factor I'm going to be using. So start with your 5 grams. I'm going to divide it by the molar mass and then put in what I know from the balanced equation. All the units out to give me kilojoules, and I have a minus 252 kilojoules. So again, 1 mole would give me 2,221 kilojoules. If I had just 5 grams, then I just have a lower amount.